Our first speaker, Gautham Vasan, PhD candidate in statistical machine learning at the University of Alberta. Gautham's research lies in the overlapping areas of artificial intelligence and robotics, designing and developing reinforcement learning algorithms and continual learning system for real robots. Up next, reinforcement learning for robots. Please welcome Gautham Vasan.
Cool. Hi, I'm Gautham. Thank you for joining my presentation today. Today, I want to talk to you about my approach towards building general purpose robots that can autonomously function in the real world. So drawing inspiration from nature, I try to motivate why it's important to respect the constraints imposed by nature and how to incorporate them into solution methods. And finally, I'm going to show you some cool demonstrations of reinforcement learning with robots. So first off, I'm interested in building robots with human-like intelligence. So that's the overarching goal of my PhD research. So what does that mean? It means I'd like to see general purpose robots that are capable of functioning and surviving in the real world, just like freely living animals. So I want robots to be able to learn on the fly by interacting with the real world. I want robots that can continually learn skills and knowledge. So once they learn these skills, they should be able to build upon these skills and keep learning on and so on and so forth, just like life. So as you might know, this is an important goal in AI and robotics. So as a community, we have been working on it for quite a while now. So first off, I'm going to point out some historic AI milestones. So one thing that's common in all these images here is these are all game playing AI. So these games involve some high level reasoning and strategic planning. So in the first image, you have Deep Blue, which was the first chess playing program to beat Gary Kasparov, the then world chess champion and a chess grandmaster. And within a couple of decades, we had this program AlphaGo from Google DeepMind, which was able to beat the highest ranking player in Go, right? And Go was thought to be unsolvable for at least a couple more decades, but we were able to solve it just in a span of 2 decades right after chess. And after that, we have this video game solving agent from OpenAI, which plays Dota 2. Some of you might be playing it here, so you know how complex that is. It takes quite a lot of time. It takes about 45 minutes for a game. You need to really think about strategy and high-level planning and cooperation here. And we had this agent which is able to beat this. Okay, so very recently, we had ChatGPT, which is a very impressive demonstration of natural language processing, right? And I tried asking some questions, and I asked it about neuralberta.tech. I'm not sure if it's visible at the end, but basically it tells me about the student-run organization here, right? So it was able to get all this information from the website. I don't know if it just memorized it or it just remembers it, but it does have this information. And when you ask it about neuralberta.tech, you have quite accurate information. So you can always make the claim, maybe it's just remembering everything it saw online. So I tried something next. So I asked it to write a poem about gummy bears, but in Old English though. Right? And it comes up with something which is actually funny and it makes total sense. It's always in context. And when I saw it, I was just laughing the entire time and I was always impressed. So this begs the question. It's like, are we actually close to building human level AI? It's like, are we really that close? It's like within a few years, are we going to see it? So next up, let's check robots. So this is again, a recent demonstration from Boston Dynamics. I'm going to play this video and it's going to be played at 1.5x speed. So the important thing to note here is there's a human who is working on this column and then he's missing his toolkit. So he's going to ask the robot for his toolkit and it's going to bring that. Okay, so first off, this humanoid robot, it sees that it can't find a way to the human user. So it reasons about the environment, gets the plank, and then fills in the gap. And then it goes for the toolkit, picks that up, and then climbs the stairs across the plank, and then now jumps to the next stage, and then flips it back to the user. And now just because it can, it's going to push off this block, jump on this, and do a backflip. Right, so just looking at this, you think, okay, so we have this natural language ability now. We have this game playing AI. We have this robot capable of cool things. So maybe we're really close. But turns out you're not. Because this video right here, this is a very carefully handcrafted demo. So the people who work here, it's like they carefully set this up, and they have all these scripts which would govern this behavior in the controlled environment. So this robot cannot function autonomously in unstructured environments. So again, these demos, they are meant to showcase the hardware and control capabilities, not AI. Again, so I don't want to take anything away from Boston Dynamics people, because this is a very impressive demo. But all this is to say, it's like all we are talking about here is hardware and control capabilities. This is not AI. You're not solving anything in an unstructured environment. So next up, I'm going to show you a video from RoboCup, which happened last year. So RoboCup, it's this competition which happens every year. Teams from across the world participate. And this is the finals of the humanoid adult-sized soccer. This is kind of an unstructured environment. So this is not 11-on-11 soccer. You just have one-on-one soccer, but you don't even block the opponent all the time. So the team in red is Korea. The team in blue is from Germany. The team from Korea is going to go first. I think this is quite an accurate representation of where we are in robotics right now in the industry or in the community. So this robot, it kicks the ball. It's quite slow. It doesn't go to the goal. And now it walks slowly towards the goal, right? And there's this human which is right behind it to make sure if the robot falls off, he's there to catch it. This is point blank range, but it still misses it. So now the team from Germany, they do a bit better. It's like the movement is a bit more fluid, but it slowly just goes towards the ball. It again needs a second attempt to hit the goal. So, right, we still miss it. So this is where we are. And it doesn't make any sense, right? It's like we have all this AI solving impressive games in natural language, but in robotics, we're still quite far behind. And part of the reason lies with Moravec's paradox. So in this graph here, it's like the x-axis and y-axis, they both talk about difficulty. So let's say algebra is easy for both, it's like undergrads, and let's say a robot, right? But then diagnostics, it's hard for both. So locomotion skills, which we take for granted, which is easy to us, it's hard for a robot. But chess, which is hard for us, it's kind of easy for a game-playing program. Okay. So part of the reason is early AI researchers, they concentrated on the tasks that they thought are difficult or challenging to them, that's stimulating to them. So abilities of animals and one-year-olds, especially learning, this was overlooked. So this deliberate process that we call reasoning, this is effective only because we have a lot of accumulated sensory motor knowledge over time. By sensory motor knowledge, I mean knowledge relating to the sensors and motor functions we have within the body. So we are exceptionally good at perceptual and motor learning, so much so that we make it look very easy. So when we think about robots doing things, we think it should just come naturally to robots because it comes naturally to us, but that's not really true. So think about tasks like walking or running, right? It's very easy to us. We don't even think about it. We learn it as babies, but for robots, it's not the case. So here, I think it's important for us to remember that the sensory motor skills, they took millions of years to evolve. Whereas this abstract reasoning, it's more of a relatively recent thing in the evolutionary scale. So all this to say, robotics is quite challenging, and we have to keep that in mind and not underestimate how difficult the problem actually is. So let's observe some animals now. So here it's like you have this dog which is trying to catch its toy. So it's like it's midair, the toy is stuck in the tree, and it's trying to catch that. So the first attempt he fails. His friend tries, now he fails too. Second time, he fails again. But this time around, he grabs it. Right? So if you just stop for a moment to think about how complex this is. Right? So it's like you have this robot, and you have this dog, which has to figure out that, okay, so I'll climb on this tree, propel myself to the side, and I'll aim properly, and then I'll grab this in my mouth, and then land safely. Think about all the complex reasoning and all the things it has to learn. So the first two times it fails, right? So it figures out that, okay, so I have to jump maybe in this angle or something and then grab this. So first, so animals exhibit purposeful behavior. In this case, a dog knows that it has to grab the toy. So the animals interact with the world only through the sensory motor interface. So in this case, there's no human telling the dog that, okay, so this is the toy you're supposed to catch. The dog just knows for itself. It wants to do this, it has this goal, figures it out all on its own. Animals can be incredibly fast and agile, often reacting in milliseconds to achieve their goal. And all the mechanisms necessary to govern the behavior of this animal, it's running on board. It's just in the brain. So the dog is not connected to some Google server, which tells you this is what you're supposed to do in the next moment. Everything is happening on board. And finally, there's no supervised learning here. The learning is all self-supervised. All this to say there's no dog expert telling other dogs that this is a cat, this is how you classify things. They're able to figure it out on their own. Okay? So this is where we are right now. It's like we have special purpose robot automation. So we have custom built robots with quite specific capabilities, and you have these expert human programmers who can code up some impressive behavior. And this gives rise to special purpose behaviors, right? So we have these industrial robots which perform very specific functions designed for efficiency. But this is what we care about. So we want general purpose robot autonomy. So we want, say, someone like a robot chef or a robot butler, which is capable of doing a bunch of different things, learn skills on the fly. But there is a missing piece of the puzzle here. And what is that? And I hypothesize that the answer here is learning. So the missing component here is learning, and we want these robots to be capable of learning different things over time. So they should progressively develop, accumulate knowledge, and then try to reason about their environments. So when we talk about a general purpose robot, like what do we mean? So I'm going to list out some characteristics here. So the first criteria is it should be fully autonomous. It receives an observation, takes actions, and learns from the environmental feedback without any human intervention. The two, it has to learn in a real-time setting. So the samples would arrive on the fly in a sequential fashion. So there would be a robot which is interacting with the world right now. It tries to understand where it's at, what the world does, and then try to reason about it. And there's no prior knowledge required. So evolution gave us some behavioral priors. It was encoded. In the same way, we can encode some behavioral priors for the robots, but that should not be necessary. We should still be able to learn over time. Such a learning agent should be sample efficient. All to say, it's like it should be able to learn within a reasonable amount of time. It should learn from relatively few training samples. The skills the robot learns should be generalizable. So the learned skills and knowledge, they should be reusable in unseen but similar tasks. So let's say you learn how to jog, right? If you learn how to jog, the robot should be able to figure out how to run in the next stage, building off that. And the learned skill should also be hierarchical. So let's say we have a robot hand which learns how to control each individual finger. Now you should be able to compose this into, let's say, how to play a chord on a guitar. Because you have finger control, you can go on to the next stage. So reinforcement learning is a natural way of formulating this kind of a learning problem. So I'm going to introduce reinforcement learning for a little bit before I go into my own work. So let's start with a simple setting. It's like in reinforcement learning, you have a clear delineation between the agent and the environment. So let's say you have a dog and his owner is asking him to retrieve a stick. So she's going to throw a stick, the dog gets the stick back, and then he'll get a treat for it. So in this case, the dog can move around, fetch the stick and come back. Those could be the actions. And the reward here is just getting a treat for bringing the stick back. And you can observe the environment. So the dog has eyes, it can sniff around, it sees what the world is. All right, so let's formalize it a bit more. So now we have an agent and an environment. The agent can influence the world through its actions. And the environment responds to the agent's actions and presents a new situation. And the only feedback this agent gets is through a scalar reward signal. So again, with this example of a dog trying to fetch a stick, the feedback you get is just the treat for retrieving the stick. So if you want to think about this mathematically, all you get is zeros at every point of time until you fetch the stick. So once you get the stick, you get a +1. And this feedback could be temporally delayed. It may not be instantaneous. So let's say you're playing chess, right? So you pick an action right now. The consequences downstream, that's not known right away. You can have a delayed response. And time really matters in this setting. This is to say actions have these long-term consequences. So reinforcement learning is this nice framework where you can learn new skills and behaviors through trial and error interactions with the world. And you can learn in structure and unstructured and unknown environments. So just to have a quick connect with psychology and neuroscience, because that's what my audience is today. So a lot of you would be familiar with Pavlov's dog, I think. So we talk about classical conditioning and operant conditioning. So with classical conditioning, it's the process of learning to predict the world around you. We ask the question, what is going to happen? And with operant conditioning, we try to modify the behavior through rewards and punishments. So in this case, we are talking about what do we do to maximize the reward? And this is about learning to control. So some of you might see the parallels already where with reinforcement learning, we can do these predictions and control. And it is based off this kind of an idea. In all the methods we use with reinforcement learning, it's like we have this fundamental idea of a temporal difference error. So if you don't understand the math here, it's okay, it's not important right now. I just want to point this out and say it's like this also has some connections in neuroscience. So some of you might be familiar with the Rescorla-Wagner model. The equation should be similar to that. And we also have some connections to the reward prediction error in dopamine, but we can talk about that after the presentation. So I want to start with some of the current reinforcement learning approaches with robots. So this here is an industrial robot arm. So this is trained to open a door, right? So there's this human who is holding the robot and going through different movements and trying to show it how to open the door. And if you see, there's a wire coming in from the door. So it's like have the sensor which tells you that the door is open or not. While the demo itself is impressive, it's like when you think about it, it's like something's off, right? It's like when you open a door, no one tells you that the door is open. You don't have a sensor which goes beep, the door is open now. You just know for yourself. And the same way, there's no one holding your hand and teaching you how to open a door. You can figure it out on your own, right? So with a lot of these approaches of this kind, they're called learning from demonstrations. So in this case, you have a lot of environmental instrumentation, which is external, which is not a part of the robot's body, which is used to define the reward function and the ground truth state. So while an approach like this might work in the lab, it won't scale in the real world. We can't deploy this to the real world. The second case, we have this nice demo of this OpenAI dactyl. It's a Rubik's Cube solving demo where we have this dexterous human hand. So dexterous manipulation was unsolved for a very long time. So this was a very impressive demo. They used an approach called sim to real, where so initially you build a simulator for the robot hand, and you train everything inside the simulator. So this was done because this hand is expensive and it's quite easy to break. So they do everything in simulation first, and then they deploy to the robot. So simulations like these, right? It's like, so the fundamental assumption here is that it's quite close to reality, which means it can be very expensive to create and model. And this accuracy of the simulation, it's also going to impact the effectiveness of the transfer. And this requires a lot of data and computational resources. So both these approaches here, while these are the state of the art, these are not going to help us get to the real world. You can't deploy this. So state of the art robot reinforcement learning approaches, they ignore a lot of crucial real world robot constraints. So I'm going to introduce 3 constraints here, which I think are necessary for any robot experiment if you care about deploying to the real world, especially if you want an animal-like intelligence. So the first has to do with the agent environment interface. So the agent should perceive and influence the world only through its sensory motor interface. So when you talked about the example in the previous slide, where there's this robot arm opening a door, it should be able to figure out on its own that it opened the door. You don't need external sensors for that, right? So others can teach and show demonstrations to influence the mind of the agent, but it should not happen by bypassing the sensory motor interface. In the second case, we need low-level control. The agent should react based on perception at a very high frequency. So we saw this dog, which was very agile. We want robots capable of doing that kind of fast movements, which means we need high frequency control. And if that's the case, we need low-level commands. We need velocity or torque commands given to the motors. So a high-level command like open the door, they would be decomposed into a series of lower-level actions in the mind of the agent. And finally, we need onboard computation. So all the computations necessary for the survival of the robot, it's like in the real world, they must happen on board. So if you're stuck because your robot is making a software update while it's in a critical condition, that's not going to work, right? So it's like everything that's necessary, it's just running on board. It can talk to the clusters when it's necessary. So I'm going to talk about some of my own research right now. So I'll be using this robot called Anki Vector. This is just for the demo purposes. So Vector is marketed as an emotionally expressive, lifelike animatronic robot pet. So it has this tiltable head, which is capable of making facial expressions. It has an arm, which is capable of lifting a cube. You have speakers, touch sensors, distance sensors, and clip sensors, and you can also control the 2 wheels. So this is Vector in the arena, and you have some colorful ping pong balls over here. So you're talking about animal-like intelligence, right? So it's like you're looking at this arena from outside. It's like as a human, you know what the right thing to do is. So let's say this robot has to go to the charger. So you have an overhead view, and then you can directly go to the charger. But let's see what the world would look like from Vector's point of view. So you have this camera. This is the point of view feed. So you have this grainy video which is coming in, and you're supposed to figure out that, wait, I'm on this arena somewhere, and I have to find the charger, go towards it, and then dock on top of it. Right? So how do you make sense of it with just these images when you don't have the overhead view? So that's the problem you're kind of trying to solve, because everything has to go through the perception of the robot. So first off, we're going to solve a simple task. I'm calling it Vector Charger Detector. So you have Vector, it's facing the charger right now. And the task is quite simple. We don't even have to dock on the charger. You just have to find the charger. So finding the charger means you're close enough to the charger. And there's examples of successes here. So that's what the final image should look like when it's close enough. So this task is, the optimal behavior of the task is difficult to engineer, but it's easy to set up as an RL task. So we're going to set this up as an RL task. So as an observation, as the input, we'll get RGB images and the wheel velocities. And we're going to control the 2 wheels. And we'll send an action every 100 milliseconds. So we get a reward of -1 every time step. So the task is done when you're close enough to the charger or when you time out. So it's like we give 30 seconds for the robot to reach the goal. If it doesn't find the goal within 30 seconds, that episode is considered a failure, and then we start over again. So we also have some additional things for failure mode set up. So sometimes Vector can get stuck. It can climb the wall and be stuck. So, okay. So we have this routine, which is going to bring it back down. So we want to discourage this flipping over. So we penalize it whenever it happens. So we want to discourage these actions. And we also have a random reset routine, which would make sure that the robot starts in a random location every time. So we're going to learn from scratch, right? Which means the robot is just going to try some random things. It's going to try some random actions and try to make sense of its world. So right now, this is a random control policy. So it's just looking around, it's observing its world. It's very close to the charger, but it can't find it yet because it doesn't know how to go there yet. And it's quite frustrating to watch because it's just like just squirming around and not doing anything meaningful. So as an experiment, if you're just sitting there, you're like, just do it, just turn around. And you want to tell the robot to do that, but it can't because it doesn't know yet. And a lot of times it's never going to find the charger. But over time, as it continues learning, right, this is what happens. So we use a method called soft active critic. And after 75,000 training steps, which is about, let's say, 7-8 hours, right? You start reaching the goal. So if you learn with these images, regardless of where you start in this environment, you're going to find the charger. So on the top left, you have the insert feed. So you're going to see the feed of the robot. Oh, which one? So this shows that we can solve this vision-based control task from scratch in real time on robots. And you can see this as one skill you have learned. So you just know how to reach now, but this can be reused later in the future. And this satisfies all the learning constraints we imposed in the learning system before. And I'm not going to show the videos of the performance on the other robots, but we had the same system, but different learning agents deployed on all these robots, and we have learning on all these cases. And finally, I want to talk about something I worked on when I was working as a machine learning researcher at Kindred. So we had this product called Sort. So Sort is this piece picking robot. It's used for parcel fulfillment in clothing stores like Gap or American Eagle. So this robot is deployed to some remote warehouse. And let's say you order clothes online, right? So all the clothes that people order, it's going to fall in this bin. And this robot, all it does is pick up an item, scan it, and store it. So you have a piece of clothing, picks it up. You see these red lights coming off. That's a scanner. So that tries to scan a barcode. So that's how you know which order is what. And each order is stored into a unique cubby. So I worked on something called RL Scan, which was using reinforcement learning to teach, to learn how to scan this item. So when you think about it, right, this is kind of a hard problem, because if you pick up a piece of clothing and if you try to move it up, it's like it doesn't move with you. It's just going to jiggle around. So because it's a deformable and manipulatable object, it's like you can't model this. So you need something like reinforcement learning to learn this control policy. And this is actually deployed in production now. So we were able to beat the baseline, and we were able to train this in a way that I was talking about before in all the slides. So this is among the first successful demonstrations of vision-based deep reinforcement learning in the industry. No one else doing it as far as I know. So I want to stop here and thank you all for joining today. And I'm happy to take any questions. Sorry, do we give a mic? Yeah.
So essentially, you showed us like a camera footage of what he sees and perspective he sees. So it kind of reminded me of how Tesla works, where they use like computer vision alongside with reinforcement learning. Is that kind of how vector works as well? Where they use like computer vision to detect the objects and does the reinforcement another one?
Sorry, if I understood the question correctly, you're talking about the Tesla self-driving system, where they detect objects first and then do reinforcement learning on top?
Yeah, so it's like kind of similar to like what Tesla kind of like works there.
Right, it's somewhat similar in the sense we still have reinforcement learning, but it's end-to-end. So we don't have a different perception system which recognizes the objects. All the reinforcement learning system sees is the camera feed directly. So you have to learn everything from scratch. So the perception plus the control policy, that's learned by one neural network.
And so how does vector know it's like that's the charging port? You have to like train it as well?
No. So in this case, we give a reward of -1 every time step, right? So which means you're incentivized to reach the goal as soon as possible. So the episode ends when you see the charger, when you're close enough to the charger. So let's say you see the charger within 10 steps, right? So the reward is going to be -10. But if you just keep waiting, it's going to be like -20 or -30. So it's just optimizing to get as low a return as, just trying to maximize the return here, right? So that implicitly encodes all this behavior.
Right.
Sure. Sorry, I didn't hear the second part.
The efficiency.
The efficiency?
That's why it gets consumed in the market, right? Because it increases efficiency.
Right. So what happens is, so you're getting this -1 every time step. So you have this notion of a time step, and this episode is what 30 seconds long. So it's like, in my case, the maximum reward can be -300 because it's 30 seconds long. What happens is, let's say for the first few times, it randomly stumbles around and finds a charger, right? So initially, maybe it stumbles upon the target, and then it gets a reward of -250, right? But that's better than getting -300. So the robot keeps trying to get -250. But then as it keeps trying to do this, it sees that, wait, I can do this in a better way. I can do this in a better way. And it keeps optimizing as much as possible. So eventually you converge to this optimal behavior, or at least that's the goal.
Would it be fair to say that the reward is more exactly chasing the charger than a specific verification?
Sorry, a specific.
Verification. The specific point in view. That's the process.
So in this case, there's a zone from where you're close enough to the charger. So as long as you're in that zone, it's like the episode is considered complete. So I think you can set up any task in this way. It doesn't have to be just reaching the charger. So in this case, we're saying you get -1 until you find the charger. But let's say you have a different object here, right? You can still do the same thing with that too. So it's always just this reward function is leading you to this behavior. So in this case, yeah, you just care about reaching a goal state. Yeah, so in this arena, it starts at any location and then it's supposed to find the charger.
So vector is vector instruction yet to be, or people like you give the students give vector instructions to those charging for, or does he like oh, my goal is to get
Right. So I'm just going to repeat the question for the video. So the question was about, do we give it an explicit instruction or is it just through the rewards?
Yeah.
So this is just through the rewards. So all we give is the reward and we don't tell the agent anything else. Yeah.
In reinforcement learning, how does the robot know that negative arguments function response? How does it interpret that?
Right. Good question. So reward functions could be different, but the goal is about accumulating as much reward as possible. It's like, so the sum of rewards, like that's what you care about. That's called the return of reinforcement learning. So this sum of rewards you get, right? So you want to maximize that. So it doesn't matter if your rewards are -1 of this one. As long as you maximize the cumulative sum of rewards, you're good. So when you think about it that way, you're just offsetting by some margin. Does that make sense?
And can I ask another question? So this robot here, was it but does it have any practical usage? And if it doesn't have a practical usage, then how can you use the information that this robot wants in your simulation will have practical usage?
Right. So in this case, so the experiments we're running here, right? So you can think of it as a litmus test. If it doesn't work here, it won't work in the real world. Right. So this is kind of an analog. So you see this robot at the gripper, right? So it can lift a cube or it can lift up a package. So you can think of it as an analog to a robot which is capable of moving around and lifting packages in, let's say, an Amazon warehouse. So before you would test that in the warehouse, you would test with something like this, and then you'd slowly scale up.
That change the
So the algorithm stays the same, but because you're using LiDAR, the data structure would look different, right? So you have RGB images, now you have LiDAR instead. So the architecture of the neural network would change, but fundamentally it should all be the same.
Is your reward only affected by time, or does whether the robot is fully facing the trigger or any?
So in this case, all we have is -1 till you find the charger. So the reward is conditional on the state. So it's if you're in the terminal state, the episode ends, you get a 0, but otherwise you're just getting -1 everywhere. So you don't have anything which is a function of the immediacy.
Great. Well, that's all the time we have.
Thank you.
Beautiful presentation, by the way.
Thank you.
Just maybe come to this one.
Great presentation, Gautham. Thank you. Those were great questions. Thank you, everyone.